Okay, so good morning, everybody. We have today we have a new edition of the doctoral meeting with the work entitled ROI Feature Propagation for Video Object Detection by Daniel Costa. So we are going to proceed as usual with about 20 minutes of presentation, and then we leave room for questions. So if you want, when you want to ask a question, please raise the hand, and then I will give the word to more or less in order to each of you. So we can start as soon as Daniel is ready. So you have the word.
Okay, thank you for the presentation. I will share my screen. I think you can see now the presentation, right?
Yes.
Okay. So thank you for the presentation, and thank you everybody for attending this doctoral meeting. Here we have the outline for the presentation. We will start with the motivation, describing the video object detection problem. Then I'll show you our first proposal to solve this problem that was published on the European Conference on Artificial Intelligence. Then I will show you an evolution of this approach that we call FANET, Feature Aggregation Network, that is currently under review in the Transactions on Image Processing journal. And at the end, I will show you the results of the evaluation of our methods, and we will discuss the conclusions. So, first of all, what is object detection? The object detection problem has to solve two main tasks. First, we have to localize the object given the bounding box that surrounds each object of interest on the image. And we have also to classify one of these bounding boxes in one of the object of interest categories, given the confidence score for the given class, as we have here. So how can we do that? There are two main approaches in the state-of-the-art: two-stage object detectors and one-stage object detectors. In this presentation, we will focus on two-stage object detectors. These methods take a set of object proposals, and each proposal is just a region of the input image where the probability of containing an object of interest is high. These methods also use a deep convolutional network to extract deep features, a deep feature map for the input image, and using the object proposal and in a ROI pooling layer, we extract a feature map with the features related with the proposal. This feature map has a size independent on the size of the input proposal. And using this small feature map, we can apply a bounding box regressor to localize the object and a softmax classification to classify the object. How can we calculate this initial proposal set? Modern two-stage object detectors typically include a component called Region Proposal Network, or RPN. This RPN defines a grid, and in each position of the grid, we test a set of predefined anchor boxes. For each anchor box, the RPN classifies it between object of interest and background, and if it is an object of interest, the RPN refines the bounding box to better fit the object. So now we have the proposals, and we can refine it and classify it in the network head, as we saw before. So how can we solve the video object detection problem? A naive approach can be applied just a single image object detector at frame level. But the main drawback of this approach is that we are not taking advantage of spatiotemporal information that we have available.
Daniel, we only see you and Felix in the main presentation, and the presentation only appears at the bottom of the, at least in my case. at the bottom of the image. So try to.
So here we are not seeing the presentation.
Yes, I see the presentation.
Yeah, but okay. In my case, I see the presentation in the bottom of the screen.
Jose Manuel, I think you just have to double click on the presentation, and it will go to the middle of the screen.
No, it goes but disappear. Okay. Okay, so if you can see, I try to follow as I can. So
I'm sharing the screen, so I don't know how to change it. We can go on.
Yeah. Please.
Okay.
Go on.
Okay, so as I was saying, with spatiotemporal information can be very valuable to solve problems such as motion blur, occlusions, or big changes in the appearance of the object. So for instance, in this example here, we have motion blur. And even though localize the object is simple or easy for us defining this bounding box, classifying the object is not that easy. And in this example here, we do not have motion blur. The object is well defined and clear, but due to the position of the object, the strain position, it's really hard to classify too. But I showed you the original video, and I hope you can see how using spatiotemporal information, viewing the object from different viewpoints help us to classify the object. And I think it's even more clear with this video. Seeing the video, it's easy to classify the object. It's a hamster. So we want to use this spatiotemporal information in our object detector to give detections like this one, where we are detecting a really challenging object with motion blur. These are real detections. This is our proposed architecture, and the main difference with a single frame object detector is that we are using several input frames instead of just one. So for each input frame, we calculate the feature maps using a deep CNN and the object proposals using an RPM. How this works? Well, instead of take a predefined set of anchor boxes as we do with single images, we define anchor cuboids. Each anchor cuboid is a sequence of anchor boxes, the same anchor box in the same position in every input frame. So now, in each frame, the RPM refines the corresponding bounding box to better fit the object in that frame. I'm seeing a message of Teams. Okay. So now I'm watching. Now that's fine. So now in each frame, the RPM refines the bounding box in the corresponding frame, giving object tubelets that link the object through all input frames. In our approach, we use a feature pyramid network. So instead of take just features from the deepest feature map on the network, we take features from several pyramid levels. So we have to give object proposals at different pyramid levels. What happens with object proposals in general in single frame object detection is this situation over here, where we have many proposals targeting the same object. So we have spatially redundant proposals. We use a non-maximum suppression method to suppress all the spatially redundant proposals, taking just the one with the highest score, as we have in the second image. In our spatiotemporal approach, we cannot do that at frame level, because if we remove boxes in one specific frame, we break the tubelets. What we do is we analyze the spatially redundant tubelets, and we remove a complete tubelet if it is redundant. So now we have feature maps at different pyramid levels. Here we have 3 pyramid levels, and object proposal tubelets. Here we have 3 proposal tubelets. Each border style represents a different tubelet. So using a Roy pooling layer, in our case a Roy align method, we extract feature maps for the corresponding object in each input frame. Now we concatenate all the feature maps, getting a feature map with a larger number of channels. A number of channels depending on the length of the tubelet, depending on the number of input frames. So we propose a new method called Temporal Polling that summarizes this information, resulting in a feature map with a number of channels depending on the number of input frames. How this temporal pooling works? It is based on an element-wise maximum, and we have an example here with 4 input frames, and we have the result here on the right. So in each frame we have an object proposal, the blue box, belonging all the proposals to the same tubelet. Below each frame we have the feature map for the proposal. Each blue square represents one of the 7x7 channel, and darker values are low activation values, and light colors are higher activation values. So we can see one channel highlighted in red, and we can see in the aggregated output that we track all the higher activation values due to the maximum. So in general, we can see how we have higher activation values in the aggregated feature map. Here we are working with channels of 7x7 pixels, so we are working at a very low resolution. That means that if the RPM do not fit the proposal perfectly, this do not affect our method. It's not that important because we are working at a very low resolution, so we do not have misaligned features due to a slight network error. Now we have spatial features for the current frame in this feature map and spatiotemporal information features for all the previous frames in this feature map. So we propose a spatiotemporal double head to solve the region classification, the object classification, and the object localization. Sorry. To perform the object localization, we only use spatial information. As we saw at the beginning of the presentation, even if the object is not well defined in the current frame, it is not a problem to localize the object for us. So we hypothesize that spatial information is enough to localize the object, while spatiotemporal information is useful to classify the object. So for the object classification, we use both. We predict the object category with spatial information and with spatiotemporal information, and we mix the predictions with equation number 3. It's important to notice that this double head component, specifically the spatiotemporal branch, is the only trainable component if we compare our architecture with the spatial baseline. I mean, if we have a single image object detector and we want to apply our methods, we only have to train this component. We can reuse all the other weights. So until here, we were working with short-term information. That's because our network takes typically from 2, 3 to 6, 7 input frames, but we want to exploit also long-term information. And to do that, we apply a long-term object linking method. For instance, here, you have a video with 2 objects and detections in every frame. So what we do is we build a tube with all the detections that contain the first object and another tube with all the detections that contain the second object. Here we have a network error in frame number 4, because we have a false negative. The network does not detect the second object. So we have two fragments instead of a long tube. Now that we have these tubes calculated, we rescore all the detections belonging to each tube, increasing their confidence. Why? Because if we can link one detection to one long tube, it's likely that this detection is a true positive. Because we can link, it makes sense in the long term. But what happens with this kind of errors that we have here? Well, we propose to use our short-term tubelets to link fragments when that happens, to overcome this kind of network error. For instance, here, if the last detection of the first fragment and the first detection of the second fragment belong to the same short tubelet, we link both fragments building a larger tube, so our rescoring method can work more effectively. So this is our evolution of our first approach, and the main difference here is this component over here, which is a reimplementation of the spatial branch of our spatiotemporal double-head approach. Here, instead of take the proposal and refine it just once, we refine the proposal several times, in this case 3 times, to get a more accurate box. That makes sense in our approach because the spatial branch of our double-head spatiotemporal approach is in charge of getting or of localizing the object. We want the most accurate bounding box possible, while the classification is held by the spatiotemporal branch. So now I'll show you some results in the Imagenet video dataset. This is the standard benchmark for video object detection. It contains around 4,000 training videos and more than 500 validation videos. Here we use also images from the Imagenet detection dataset to increase the training set to have more examples. Here we are not detecting person because person is not one of the objects of interest categories in this dataset. In fact, here all these people is like more a distractor for the detector. Here we have many detections and the network, many occlusions, and the network is able to detect the object. We have also fast-moving cameras like this one, and this dataset contains many videos with fast-moving objects like these ones. And if we extract just one isolated frame from these videos, we will have a significant amount of motion blur, as we have in the first video that I showed you in the presentation. So, using this dataset, we evaluate how each component contributes to the mean average precision. The mean average precision is the standard metric for object detectors in general. So we can see how using just the spatial classification or using just the spatiotemporal classification underperforms the use of both. That means that both spatial and spatiotemporal classification are complementary. We can see also how adding the cascade, we increase the map, the mean average precision in every case, and how adding the long-term object linking, we increase further the mean average precision using the cascade and without the cascade. Here we analyze how the number of input frames affects the network precision. In the graph on the left, we are training and testing our framework with the same number of input frames. For instance, here we are training with 3 input frames and we are testing with 3 input frames. In the graph on the right, we are training always with 2 input frames and we test with 2 to 9 input frames. For instance, here we train with 2 input frames and we test with 4 input frames. Here we are not applying the long term of the linking, just short term. And we can see how changing the number of input frames do not affect the network behavior that much. And we can also see how increasing the number of input frames from 2 to 6, we are able to increase the detection precision up to 76.9. Here we compare our method with the state of the art. If we compare our method with our single frame baseline, we improve the performance by more or less 3 points using short and long-term information. And if we apply multi-scale testing, we boost the performance up to 80.9, which is better than all previous works in this widely used Imagenet video dataset. Now I'll show you the results of the execution of our network in a different dataset, the small targeting detection database. This dataset was built here in the CITIUS, and it's focused on small objects from 4x4 to 16x16 pixels. These objects are really small, and it's a really challenging dataset. As you can see, the objects are completely different than the ones we have in the Imagenet video dataset. In this dataset, we outperform our single frame baseline by 4 points using just short-term information, and by 5 points, more than 5 points, using both short and long-term information. So as a conclusion, we have proposed a new network architecture that takes advantage of spatiotemporal information to improve the object detection. We have proposed a short-term object linking method to link objects in the short term. We proposed a new temporal pooling operator to summarize the data, the spatiotemporal data, and we proposed a new spatiotemporal double-head architecture to take advantage of both spatial information in the current frame and spatiotemporal information. We also propose to include short-term information in the long-term object linking methods to overcome network errors, and with these improvements, we achieve state-of-the-art results in the widely used Imagenet video dataset, and we improve our baseline in the small target detection database by 5 points. So that's all. Thank you for your attention, and if you have any questions, I'll try my best to answer them.
Thank you for the presentation, Daniel. So now is the time for questions. So if you have any question, please raise the hand, and I will entrance to one by one. So any questions at the moment? Yeah, while they are preparing some questions, I would like to ask, okay, you take into account or spatiotemporal coherence implicit in video. Mm-hmm. And okay, so there are a kind of networks, the LSTM networks, recurrent networks that was probably introduced in natural language processing. So okay, there is some kind of similarities between your approach and the idea that was presented in this network. So I would like to comment something about the similarities. Or
yeah, LSTM work with a short and a long-term memory too, but in the state of the art, many works have been trying this kind of networks to solve the object detection problem in videos, but it seems that they not perform that well, that those approaches that manage to aggregate features like we do. I mean, in the state of the art, it seems that the standard approach is aggregate features more than in convolutional neural networks, more than use these recurrent neural networks. It seems that it doesn't work. Despite, if you analyze it, it's like the most direct approach because they were designed to solve this kind of problems with temporal information, but it seems that it doesn't work that well in object detection.
Yeah. Okay, but anyway, it was probably it could be more useful in the location. Probably not for the recognition, but in the location of the object. I don't know.
Yeah, not for the classification, but for the localization.
Yeah, yeah.
Yeah, it can be. I've not. Okay, I haven't tried because it's in the literature. It's almost clear in every work that this convolutional approach is better. So I can tell you because I haven't tried, but the numbers in the Imagenet video dataset are higher with this kind of approach.
Yeah. Okay. Thank you for the answer. So, any question? Anybody have any some questions?
Jose,
Yeah.
there is a question at the chat by Lorenzo Vaquero.
Sorry.
You can read it, or he can just turn on his camera if he has one. If he doesn't,
okay.
he can just read it.
Okay.
Yes.
Can you hear me?
Yes.
Yeah. Please.
Okay. First of all, thank you very much, Danny, for your very nice presentation. It was very good. And I have two questions. First of all, due to the tubular linking, can we formulate your approach as a combined detector and tracker?
Well, we can use this link information to link to associate data in a tracker approach, I guess, but I don't think it's that accurate because we are linking proposals, not the final detections. So I don't think it's that accurate. But I'm not sure. I haven't tried.
Maybe you should run a test because it looks very promising.
It's why we use it here. Here in the long-term object linking, we are somehow tracking the objects through the complete video. So use this short-term information help us to solve some problems, but it's not to track the objects,
Okay. And second, what is the speed of your architecture?
Okay, currently we have an unoptimized implementation, I think, because we are working at 2 to 3 frames per second, but I really think that it can go much faster because right now I will say that more than 50 or 60% of the time is wasted in the tubelet non-maximum suppression because it is implemented on CPU, not on GPU. So I think we have room for improvement there.
Okay,
in fact,
very nice.
We are implementing it, and now it's about 10 frames per second, even though the results are not the same but it's about 10 frames per second now.
Okay, it looks very promising. Thank you very much, Danny.
Thank you for the question.
Okay, more questions? Yeah, I was a question related to the previous one because it seems a little bit strange not to include tracking, some kind of tracking
In the short term, you mean?
Yeah.
Okay, the point is that in the short, okay, each RPM produces around 2,000 proposals in each frame.
Yeah.
So if we apply a robust tracker, it can be not suitable for that problem because there are too many objects and it could be really slow. So our approach, just linking using the same anchor in the same position in every input frame, is almost free. We are linking just by position of the original anchor, so it's much faster. It's the risk.
Okay, thank you. Some questions, some more questions? So, okay, it seems that we don't have any more questions. So I find it quite very interesting, but probably most of the people is a little out of the this line of research. So it's quite interesting, of course, for me, because I am in the field, and results are really very good. So I have to congratulate you and your supervisor for the good work that you're doing. And okay, I don't know. We have to. You can leave the presentation here.
I don't know really.
And there's not more questions. I don't find any in the chat, or nobody raise hands. Is any other questions in the chat?
You can finish the Doctoral meeting now if nobody else wants to say something. So
yeah. Okay, then we finish the presentation of today. Thank you very much to Daniel for nice presentation. It's really very good work you are doing with your supervisor. So congratulations, and we need. We'll see again soon. I hope in the cities. So we finish the presentation here, and
Okay.
So Andres.
Yes, thank you very much, Daniel. Thank you very much, Jose. Thanks everyone for participating in this doctoral meeting. So we'll see each other around, maybe online or at CITES, hopefully.
Okay, bye.
Take care, everyone. Bye-bye.